Another type of chemical reaction is an acid-base reaction. We're also going to talk about gas evolution reactions. So the precipitation reactions we just talked about, you mix two solutions, it forms a precipitate, solid. In an acid-base reaction, which is also called a neutralization reaction, we have, as the name suggests, an acid and a base that react with each other. They neutralize each other, and they produce water and generally a salt, a soluble ionic compound. Gas evolution reactions, they produce gases that weren't there before. The gas that's produced is often seen as bubbling or fizzing. These are categories of reactions. A reaction can fit into more than one category. Just like anything that we classify can fit into more than one category, right? Classify vehicles, and my Forester counts as a four-wheeled vehicle, a sport utility vehicle, a gas-powered vehicle, a four-door vehicle, right? It fits into several different categories. It also fits into the silver-colored category, right? So reactions can fit into more than one category. So the acid-base reactions. There are multiple definitions of acids, and they are all correct. We just use the one that's most convenient for what we're talking about. So this definition is the Arrhenius definition, and I don't care if you remember the name Arrhenius or not. We should just understand this definition, which is really not very different from what we learned in nomenclature. An acid is a substance that produces hydrogen ions in aqueous solution. So we learned that HCl, AQ, should be named as an acid because it starts with H and it's dissolved in water. When this is dissolved in water, it is a molecular compound, but it forms ions when it dissolves in water. Really what's happening is the hydrogen ion from the acid molecule gets donated to a water molecule. So here we have our little water molecules, and here is a water molecule with an extra H on it. So the HCl donates its hydrogen to one of the water molecules. I think of the water molecules as being a little bit like a babysitter, and the hydrogen ion is a baby, right? And so chloride needs a break from the baby, and so she passes the baby off to a water molecule. So we have H plus H2O liquid gives us this H3O plus. That ion has a name. It's called the hydronium ion. We often use H plus and H3O plus interchangeably, but the truth is that hydrogen ions are not found alone in aqueous solutions. Just like when you came to school today, you probably didn't see any 3-month-old babies hanging out on the sidewalk, right? Why not? Because they're too little to be out by themselves. They can't walk, right? They're too little to be out by themselves. Hydrogen ions are too little to be out by themselves because a hydrogen ion is just a proton, right? It doesn't even have an electron, it's just a proton. So the hydrogen ion is never alone. So it was with chloride, and when this ionizes, the hydrogen ion is going to go ride on a water molecule, piggyback, or holding it, whatever, however you want to feel about that. When we use hydronium, the formula in chemical reactions, then we also have to include water as the reactant, and it makes the whole chemical equation a little bit unwieldy and complicated sometimes. And so we'll often just say H plus aqueous, and we understand that the hydrogen ion is not by itself, it's actually on a water molecule. Just like we understand that if you say you saw a baby, you probably saw the baby with someone, right? They weren't out by themselves. So a hydrogen ion is just a proton. A polyprotic acid has more than one ionizable proton. So it has more than one hydrogen that can be released. Those are released one at a time, sequentially. Sulfuric acid, H2SO4, has 2 hydrogens up here. The ionizable hydrogens are always written first. So 2H, there's 2 of them that can come off. This is called a diprotic acid. So it can lose 1. When H2SO4 loses 1 hydrogen, we get the hydrogen ion and we get the hydrogen sulfate ion. This ion can also lose a hydrogen, H plus aqueous plus SO4, 2 minus aqueous. But they do that one at a time. Any questions? Arrhenius also has a definition of a base. A base is a substance that produces hydroxide ions in aqueous solution. So NaOH. This is a soluble ionic compound, and when you dissolve it in water, the ions dissociate. They separate from each other. We've got sodium ions and hydroxide ions. Most of the bases that we will be looking at are metal hydroxides. So metal with hydroxide is probably a base. There are some bases like ammonia. You might look at ammonia and think, well, that doesn't look like a base. There's no hydroxide in there. But this can form hydroxide ions by pulling hydrogen ions off of water molecules. So what happens with this one, NH3 aqueous plus water you can think of the ammonia as saying, you need a break. I'll take the baby from you. No, seriously, really, I'm taking the baby, and we've got hydroxide left. So the ammonia takes the hydrogen, leaving hydroxide ion. So that fits the definition of this as a base. It produces hydroxide ion in solution. Some bases can produce more than 1 mole of hydroxide per mole of base. An example is strontium hydroxide. This is SrOH2. This is an ionic compound. When it dissolves, it separates completely. It's a strong electrolyte, and so we get strontium ions and 2 hydroxide ions. So we're going to get 2 moles of hydroxide per mole of the base. It's a little different than diprotic acids where it loses 1 hydrogen and then it loses another. The bases just separate completely all at once. So in an acid-base reaction, we have the hydrogen from the acid reacting with the hydroxide from the base, and those make water. So H plus OH minus makes H2O. Hydroxide really is a water molecule that handed a proton off to somebody else to hang on to for a while. And so this is the proton, the baby coming back to the parent, and now we've got the intact unit again. So when an acid reacts with a base, here we have an acid HCl, and here we have the base, NaOH. The hydrogen ion from the acid reacts with the hydroxide ion from the base to make water, and then we have these guys left. And really what this is it's the same kind of reaction that we saw with the precipitation, where we look at the ions that are formed and we swap partners. So let's put H plus and OH minus together and Na and Cl together. So we're going to get Na plus, Cl minus, H plus, and OH minus. So when you have to predict the products of a reaction, which you will have to do fairly often, a good first step is to think, well, can I separate this into ions and just swap the partners and see what I get? That works for a lot of things. When I do that, I get H plus and OH minus, which if I'm not really thinking very clearly, because it's too early in the morning or something, I might look at this as two ions and say, well, there's a positive and a negative. I need one of each. I'm going to put them together and I'm going to get, wait, that looks weird, right? What? Oh, that's water. We usually write it like this. Okay. So you should recognize that when you get these two ions together, it makes water. Then over here, sodium and chloride. I'm going to have sodium chloride. It's aqueous. There's our chemical reaction. If we look at the Netionic equation, which I really wasn't planning to do this, but I guess I can with this. So I'm going to stretch this out a little bit. No, that's not going to be good. Other things are going to move. This is plus and plus and plus. And this is a liquid, so that one's a unit together. And then these two are aqueous. So I'm kind of making just like a rough, complete ionic equation down here. So I can see what's changing and what isn't. So sodium was by itself to start with, and it's still by itself. It's aqueous, right? So the sodium ions are spectators, and the chloride ions are spectators. The hydrogen ion and the hydroxide ion became part of water, which is a liquid, and so it's not written as separate ions. So we end up with this net ionic equation of H plus OH minus gives us H2O. This is the net ionic equation for most acid-base reactions. Any questions? Yeah. Well, that's a good question. Why did these two go together and form a solid? They actually didn't form a solid. Oh, why didn't they? Because they don't. So, I mean, really, it goes back to the list of solubility rules. Sodium really doesn't precipitate with anything. Sodium is just not into, afraid of commitment, I guess. Chloride is very picky and will only commit with lead and mercury and silver. Those are the only two guys she'll go for. Nobody else. And it would be great if I had, a nice set of simple rules to explain why that is, but there isn't one. And so the best we can do is we looked at the solubility rules, and that's what we came up with. Any other questions? Here's an illustration looking at that reaction between HCl and NaOH. So here we have HCl, and when this gets into solution, we have chloride ions. We don't have hydrogen ions floating around by themselves, but they're here, they're riding on water molecules because they're too small to be out by themselves. Here we have sodium hydroxide, we have hydroxide ions and sodium ions. When these two mix together, what happens is this hydronium ion says, hey, you're missing a hydrogen ion. I've got this extra one. How about I give this baby to you and then we'll both be the same, right? So that's what it does when we get another water molecule, which just disappears into all the other water molecules. And then we've got sodium ions and chloride ions that are just hanging out. So this is a list from your book of some common acids and bases. Well, maybe I'll do it this way. These are the strong acids. You should remember which ones those are. So there's 6 strong acids. Any other acid is a weak acid. So you remember the 6. If it's not one of those, it's a weak acid. For the bases, a lot of these are metal hydroxides. Some of them have 2 hydroxides, some just have 1. These are all considered strong bases. They are ionic compounds. They separate completely into ions. Ammonia is the only weak base that you need to remember. That's a weak base. I drew this equation for you earlier, but it's also down here. NH3 reacts with water, pulling a hydrogen ion off the water, and that's how it produces hydroxide ions. This is the double arrow showing that it does not go to completion. It's an equilibrium. So this problem is asking us to write a molecular and a net ionic equation for the reaction that occurs between aqueous HBr and aqueous LiOH. So they're giving us the state, aqueous, and they're giving us the formula for the compounds, so that's kind of nice. Saves us a little bit of time. So I've got HBr, aqueous, and I have LiOH, aqueous. Once you become familiar with this, you can just swap partners and put them together without writing anything down. But in the beginning, which is now, we should write stuff down so that we can keep our train of thought and not forget what we're doing. I'm going to separate these into ions, and I'm going to swap partners. So I'm just going to write myself some little notes down here. I've got HBr, I've got H plus and Br minus, and I have lithium and hydroxide. And then I say, okay, we're going to swap partners and see what happens. So in my products, I'm going to have H plus and OH minus. And I should recognize that that forms water. What's the state of water at room temperature? Liquid. Why isn't it aqueous? What does aqueous mean? Dissolved in water. Can water be dissolved in itself? Not really. The other one would be lithium and bromide. I look at the charges, I predict the formula. Is that compound soluble or insoluble in water? Soluble. All lithium compounds are soluble. So I'm going to write aqueous. And I need a plus here. So I've got all the pieces of my molecular equation. I need to make sure it's balanced. So here I've got 1 hydrogen, and there's another hydrogen kind of hiding over here. So that's 2 hydrogens, 2 hydrogens. 1 bromine, 1 bromine, 1 lithium, 1 lithium, 1 oxygen, 1 oxygen. Cool. It's balanced. That's the molecular equation. It also asks for the net ionic equation. If I'm careful in how I write my little notes down here, I can turn this into a sketch of a complete ionic equation. This is what I did not do very carefully in the previous example. These are aqueous, they're separated into ions in the complete ionic equation. This is a liquid, so that just needs to be H2O liquid in my complete ionic equation. And then here's an ionic compound that's dissolved, and so those are separate. And then I can look and see, well, what didn't change? Who's spectating, just watching what's happening? Lithium and bromide. So I've got bromide over here and bromide over there. And I've got lithium on both sides. So the net ionic equation, which we sometimes call NIE, net ionic equation, is going to be H plus, aqueous, plus OH minus, aqueous, to form H2O liquid. Mm-hmm. Yep. The acid and the base neutralize each other and make water. That's exactly what's happening. Any questions? This one involves a weak acid. Write the net ionic equation for the reaction between aqueous HCHO2, and it specifically says a weak acid. It also has it up in the title, and if we find this in the list of acids, it's not in the list of strong acids. So this is a weak acid. So we've got this and NaOH, and we're supposed to write a net ionic equation. So I've got HCHO2. So that's aqueous. And I've got sodium hydroxide that's aqueous. And those things were told to me in the problem. To predict the products, I look at what ions do these things form, and I swap partners. This is an acid. It's one you maybe haven't seen before, but the way acids are written, any hydrogens in the front are the ones that are going to come off as hydrogen ions. So this is going to make H+, and then without the H+, what's left? CHO2. And that may look strange to you. It's okay. That's just what it is. You take off the hydrogen. Everything else is one ion. And what's the charge on that ion? -1. Because this ion is with one hydrogen ion. Together they are neutral. So this one's H+. This is what's left with the charge that it needs to have. Na+ and OH-. And I'm going to swap partners again. So this is maybe getting a little familiar. I'm getting H+ and OH-. Those are going to make water. And then my other two things are sodium and that weird looking guy, girl, I guess, CHO2-. We didn't learn how to name that. It's not in your list of polyatomic ions, but it's still a thing. So +1, -1, we just need to put them together to make this compound NaCHO2. Is that going to be soluble or insoluble? Soluble. How do we know that? Sodium compounds are always soluble, no exceptions. So it doesn't matter if we can't name this anion. We've never seen it before. There aren't any exceptions, so this one's aqueous. So what I've done here is I've written a molecular equation. Did it ask me to do that? No, it didn't. But I need to identify what happens to these things so that in an ionic equation, I know what's going to be present as ions and what isn't. So I'm going to use this as a sketch for my complete ionic equation. Here I have something that's aqueous. And so my first instinct is show it as ions, except this is a weak acid. Weak acids are weak acids because they only ionize a little bit. My Chem 1B students are learning a lot more about weak acids, probably more than they want to learn. But we just looked at the percent ionization of a weak acid last night, and it was less than 1%. So only maybe 1% of these molecules actually form ions. 99% of them just hang out as molecules. And so we're going to show this as it is mostly. So a weak acid does not get split into ions. So this we're going to have to consider as a single thing. That's our weak acid. Here, this is an ionic compound, and so that's going to get shown as ions. So I've got my sodium and my hydroxide. Over here, do I show H2O as ions? No, because it's a liquid. I'm going to show that together as H2O liquid. And what about these two? Separate or together? It's aqueous, so if you're just flat out guessing, you should guess ions. Because the only time you'll be wrong is with something like this, a weak acid. This is an ionic compound. A metal and a nonmetal, it's soluble, so that's written as ions. So then I can look what's the same on both sides. Na, sodium. So the sodium was watching, didn't get involved. Anything else? Remember when we're looking at this to cross out ions that these ones I circled in red, those are together. We can't look at this separately anymore. This is the H. Well, I guess you could say I spelled it wrong. I wrote it wrong. I left out the O. So we're not thinking about these or these. Those are joined. So is there anything else? This means no. There's nothing else. So I'll copy down what I've got. That's HCHO2, aqueous, plus the only thing left over there is hydroxide ion. And that's going to form water and this weird ion. It's formate, if you care. We should always double check to see that it's balanced. Here I've got a total of 1, 2, 3 hydrogens, and I've got 2 plus 1 is 3, 1 carbon, 2 plus 1, 3 oxygens, 1 plus 2, 3 oxygens. So this is my net ionic equation. Any questions? When we look at a net ionic equation, I've got negative ions here and negative ions here with no partners. We didn't write the partner because it doesn't matter who the partner is. There is a partner. It was sodium, but it could have been lithium, ammonium, possibly lots of other things. It doesn't matter. And so here we're just showing the people that were involved in something, not the people that just were hanging out. So here's the titration, which is what you needed for the worksheet questions that I had in the wrong worksheet. So we'll start a little bit on this. In a titration, we take a substance in solution where we know the concentration, and we react it with another substance where we don't know the concentration. And the idea here is that we want to find the unknown concentration. We add one solution to the other until we get a stoichiometric ratio, the ratio from the balanced chemical equation. That is called the equivalence point. And then we can calculate the unknown concentration using stoichiometry. It ends up being a solution stoichiometry problem. The problem, though, is how do you know when you're at that stoichiometric ratio? You know, maybe you have an acid and a base and you're adding some base, and how do you know when you're at that right point? Well, we need some help with that. So for an acid-base reaction, we can use an indicator. An indicator is a compound that changes color depending on whether it's in the presence of an acid or a base. So we can add the unknown, well, we can add the one solution to the other until we see the color change, and then we know that we are very close to the equivalence point. For an acid-base reaction, at the equivalence point, we have the number of moles of hydrogen is equal to the number of moles of hydroxide. So here's drawings and pictures. This is the Netionic equation. Hydrogen ions and hydroxide ions making water. This solution in the burette might be sodium hydroxide, and in the flask might be hydrochloric acid. It doesn't matter what those ions are, though. So we have our base in the burette and we have our acid down here. Typically, we know what the concentration of the base is, and we're trying to find the concentration of the acid. So as we add hydroxide ions from the burette, those hydroxide ions will react with the hydrogen ions, hydronium ions, that are present here. And when we get to the stoichiometric point where we've added the same number, actually it's a tiny bit more, when we have a tiny bit of excess hydroxide ions, the indicator will change color and tell us, you're done, you need to stop. This is kind of what it looks like. It looks like we're adding water to water. After a while, we're going to start seeing some pink color, but if you stop and mix it, it will go away. And at the end, it'll turn pink. We don't want it that pink. That's for, illustration purposes. This indicator is called a phenolphthalein, and it changes from colorless to pink. So let's do this acid-base titration calculation. So the titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution. To reach the equivalence point, what's the concentration of the unknown solution? I need a balanced chemical equation, which is what we just learned how to do. So I've got KOH, and I've got H2SO4. So I'm going to write the equation for that first. So I have H2SO4 plus KOH I did write it. See, I wrote it here. Technical difficulties. I need to predict the products. What two ions does H2SO4 make? H plus and sulfate, SO4 2 minus. We want to take all the hydrogens off. And KOH is potassium ions and hydroxide ions. And to predict the products, I'm going to swap partners. So I'm going to get H plus and OH minus, which I should recognize as water. And I'm going to get K plus and SO4 2 minus. And to make a neutral compound out of that, I need 2 potassiums for every sulfate. We're a lot less concerned with are things soluble or insoluble here because they're almost always going to be soluble. So any questions about how I predicted the products? Okay, I'm going to get rid of those notes because I need that space for something else. Is this equation balanced? No. What jumps out at you that's not the same on both sides? The potassium, right? I've got one potassium here and I've got 2 over there. So I could fix that easy enough. I could put a 2 here, and I've got 2 potassiums and 2 potassiums. Sulfate is a polyatomic ion. She didn't come apart. She stayed together. I have sulfate here and sulfate there, right? Let's look at the hydrogens. There's 2 hydrogens here and 2 here. So that's 4, and over here I only have 2. So I need to multiply this by 2. And then that's going to take care of the oxygens as well. This is a diprotic acid. It's got 2 hydrogen ions. It's going to give me 2 water molecules. And it's going to need 2 moles of hydroxide. So there's my chemical equation. Now I'm going to take the numbers from this problem and write them underneath, just like I do with other stoichiometry problems. So I have 20 milliliters of the sulfuric acid solution, and it says it reacts with or requires 22.87 milliliters of the KOH, and it gives me the concentration, 0.158 moles per liter.
Why did we write whether it was aqueous or not? Because it was not to be aqueous?
We could write aqueous and liquid and the state symbols for everything. I didn't because it wasn't necessary and it wasn't specifically asked for. But this is aqueous and this is aqueous. It never hurts to put those in. What am I trying to find? The concentration of the H2SO4. It doesn't specify a unit. What does it probably want? Molarity, moles per liter. So, molarity equals moles of solute divided by liter of solution. If I want to know the molarity of this H2SO4 solution, I need to know how many moles of H2SO4 and how many liters of solution. Do I know either of those things? Yeah, I have the volume in milliliters, which I can convert to liters. So that's going to be 0.0200 liters. So converting between milliliters and liters can be done in your head. You're moving the decimal point 3 places. Just make sure you move it in the correct direction. And to double check that, think about your 10 mil graduated cylinder. Think how big that is, and think of a 2-liter bottle of soda, right? So if I have 20 milliliters, that's 2 of those little cylinders, right? So is that going to be 0.02 liters, or is it going to be 200 liters, right? It can't be 200 liters, because that would be 100 2-liter soda bottles. That's way bigger, right? So if you want to do this in your head by just moving the decimal point, you can think of those things to make sure you don't get it backwards. Or write the stupid thing out every time.
So that number is the same thing as like 20 times 10 to the negative third?
Yes. So that's one way we can convert, just kind of in our heads. We can also write it out the long way. We end up with 0.0200 liters. Another way you can do this, maybe I'll do this one in purple. 20 milliliters. Well, I know what milli means, Milli stands for times 10 to the minus 3. So instead of writing milli, I'm going to write what it means, times 10 to the minus 3 liters. Now, is that in proper scientific notation? No. Will your calculator understand it? Yes, it will. So I'm actually going to put that up here because 20.0 milliliters. Okay. How do we find out the moles of sulfuric acid? The stoichiometry, right? So we know that we're going to have 1 mole of sulfuric acid for every 2 moles of hydroxide. We know the volume and the concentration of the hydroxide. So essentially what this is grams to moles to moles to grams. But instead of grams, we have a volume. So we've got a volume of KOH. We can find moles of KOH. We can find moles of H2SO4. Do we need the grams of H2SO4? No, we're trying to find the moles. So we don't need that last step. So I've got volume of KOH, 22.87 milliliters KOH, times in a line, going to moles of KOH, times in a line, going to moles of H2SO4, and I'm going to stop. Bless you. Moles of KOH down here, so those cancel out. And now I've got a little bit of an issue with units here because this is moles per liter. So if I put liter down here, the liter and the milliliter aren't going to work out. But what if I pull this same trick that I did up here? Come on, arrow. There you go. So instead of milliliters, I'm going to write times 10 to the minus 3 liters. Then liters cancel liters. If you feel better starting with milliliters and putting in a term to convert to liters, that's fine. That is perfectly good. So moles per liter, that's my molarity that I was given, 0.158 moles per liter. And then this is my mole ratio. H2SO4, there's 1, and KOH, there's 2. So 22.87 EE minus 3 times 0.158 divided by 2. And I should have 3 significant figures. I'm not done yet. That's my moles of sulfuric acid, so I'm going to stick that up here. 0.007269 moles. You didn't?
I got 12.8.
Well, let me check because I make mistakes. Yeah, degrees and radians and stuff shouldn't matter for this. Well, that time I got a different number. That time I got 0.00180673. So then what I do is I go for best 2 out of 3. 22.87 EE minus 3 times 0.158 divided by 2. Yeah. Okay, so I screwed up the first time. That won't be the last time that happens. Thanks for catching that. 0.0018067. So I gotta fix that up here. I'll go back and look at the history of my calculator and figure out what I did wrong. Probably missed a number or something, who knows. So this is how many moles of sulfuric acid were in my solution. I figured that out because I know the volume and the concentration of hydroxide ions that were needed, and the volume of the solution I measured. They just told me it was 20 milliliters. So I've got this 0.0018067 divided by 20 EE minus 3. And I get 0.09036 with 3 sig figs 0.0903 moles per liter of capital M. Any questions? Yes?
Do you know what it is to do it as well, like conversion factor? Because when I did it on the worksheet, like molarity times moles to molarity, and I just times 1 over.
You can do that, yes. So what she's saying is instead of having this equation up here, you can do this and then here multiply by 1 over the volume in liters. That's absolutely fine. A lot of people find that confusing because none of these other terms are like that. All of these other things, the numerator is equal to the denominator, and when you do that, you just have a unit in the denominator. So if it makes sense to you, go right ahead. That's what I would do when I'm writing it out, but it's confusing to people, so I don't do it in class. Any other questions? .0903. Is this a dilution problem? You see anything about diluting something in here? No. This is not a dilution problem. So I should not use the dilution equation. M1V1 equals M2V2. It's not going to work here because that doesn't include the mole ratio. If your coefficients are the same, they're both 1, the dilution equation will give you the correct answer. But then you won't learn how to do it the correct way, and on the exam, where I'm going to give you a problem where the dilution equation does not work, I guarantee that, you're going to get the answer wrong. And so again, if you're with a tutor or somebody who says, oh, well, you can just use the dilution equation for that, say, no, could I have another tutor, please?